time. All right, so who's going to be leading this awesome session today? So I'm joined by my colleagues, Samir and Timothy, both on our ML teams, on the research and engineering team. So they're building the products, they're building the VLM capabilities. They've trained dozens, hundreds of models. These are your experts. So everything you want to know about Gen AI and VLMs, these guys have done it, and we'll be sharing all of our best practices, insights. I'm Michael Ortega, I lead marketing here at Predibase. I'll be your host. All right, so kicking it off, why are we actually here today, right? We're here to talk about VLMs, and really like one of the biggest, I think, emerging trends in generative AI right now. So even more broadly speaking than just vision language models, multimodal models. Gartner predicts that by 2030, 80% of enterprise software will be powered by multimodal AI capabilities. And I don't think this is just fluff. It might sound a bit ambitious, but even if you look at today in the market, there's already tons of examples of use cases where organizations are using multimodal AI. Think about Amazon as an example. Today, you can do visual search, so you can upload text and image and find products that you want. Duolingo recently added capabilities where it's a language learning app where you actually have to describe images now in a foreign language. So they're creating deeper learning experiences. So multimodal, it's not a new thing, but it's definitely becoming a popular thing. And this is definitely reflected as well in the developer community. The teams are actually building, like many of you who are on here, building these AI capabilities. Obviously, the latest models like Llama 4, Gemma 3 all have multimodal generative capabilities kind of baked in. But if we take like a subset of some of the open source models and look at GitHub stars as like a proxy for popularity, I think there's a couple interesting trends. One, just Clip, which is more of your traditional vision model, not necessarily what you would put in like the sort of LM category. But if you just look at the popularity of Clip over the last 5 years, it's been growing pretty rapidly and steadily. And I think what's even more interesting is if you look at that green line, this is one of the more popular multimodal models, open source models, Janus, which came out from DeepSeek in late 2024, and they came to have the pro version come out at the beginning of 2025. That like incredible straight up growth in popularity, 15,000 stars in just a matter of months. So it's not just Gartner saying, hey, these things are coming, or a few select use cases out there. Developers, like many of you, are actually using these models, and the number of open source models and the use is growing pretty rapidly. But like, why do we actually care about multimodal AI? Why does this even matter? Well, when you bring in these different image modalities, there's a lot of benefits. For one, you're going to get richer context and better context understanding. So think about healthcare use cases. If you're, a practitioner who's scanning medical images to diagnose cancer, you're looking at, radiology scans of the lung. If you know that have text data and metadata on that patient, that they're 60 plus, lived in a metropolitan area with high pollution, lifetime smoker, that data plus the image data is going to give you better understanding of the context of that patient, better diagnoses. You can create more human-like experiences, right? So imagine you're using like an AI assistant for cooking, and you can both describe what you want to cook, the ingredients you have, and then show video to see if you're cooking properly. So you create an experience that's more human-like for your users and your applications. Obviously, accuracy is going to improve when you have new data points. We have a customer, Converse now, who does like supports systems for audio and video systems for drive-through. So imagine if you're in a drive-through setting and you have video, not just audio, and you have an AI agent that's helping on the drive-through. And if you can see that you have video and see this the driver's not the one speaking, and it's actually the kid in the back who's yelling, "I want more ice cream." You blend out the audio data. You know that hey, the driver's not actually ordering ice cream from McDonald's. We actually know that it's the kid in the back. We're not going to add that to the drive-through order. So having more data means better results. Obviously, more use cases. You can do cooler things, like we mentioned the retail use case at Amazon, being able to upload like a picture of a pair of shoes and describe the outfit you want to wear and the type of weather. You can now get better recommendations. And finally, you're just going to get deeper understanding from your models. They're going to really understand, what you're trying to achieve, come to better predictions. So all these things combined, there's many benefits. And what that means ultimately for you as practitioners, right, is that you're going to be able to build better applications. So I think we're all sold on multimodal. It's a growing trend. There's lots of applications, a lot of cool things you can do. And today specifically, we're going to dive into VLMs and vision language models and how to improve those models, how they function, and really help make you pros. So I'm going to pass it over to Samir to take it away from here.
So yeah, we're going to talk about VLMs, and first we're going to get an idea of what they are, and then look at some of the use cases and issues with them. So go to the next slide, Tim. So when we talk about VLMs in this talk, we're going to talk about language models that can see. So they can take an image or text, and generally a combo of both, as inputs, as the prompt, and they can output text. And this is actually a general enough paradigm to do all sorts of tasks. So we see with this one cat image, there's different tasks you can do, and even these models are trained to do segmentation where they output coordinates that let you like do some of the more traditional things that like CNNs used to be used for. So they really have a variety of use cases. Go to the next slide, Tim. Yeah. So how these VLMs are actually built, if we want to talk about the architecture, is they typically contain three components. There's the image encoder, which is a deep and fairly large model. There's a multimodal projector, which um, does a little transformation over the image embeddings that come out of the image encoder. And then there's a text decoder, which is the same as like the just raw text to text LLM. And usually is still the biggest component of all multimodal models and VLMs as well. And oftentimes even in training, you don't necessarily need to fine tune the pre-trained components. Even just training this translation projection layer can get really good results. So now let's look at like the most powerful components of VLMs, the text and image encoder. So these are generally initialized from large pre-trained models. So a very typical combo of models is like a clip-based image encoder. So for people who don't know about clip is like a transformer-based image embedding model, essentially released by OpenAI years ago, and it's still very popular. And there's variants built with a similar architecture, where you put in an image and you're gonna get representations that are also um, connected to the text that would like the text-based representation, and the LLM could be like a Qwen-based model or a LLaMA-based model. And typically the text-based decoder portion is, 10 or 20x larger than the image encoder. So it's still the main backbone of your model. And really VLMs and most multimodal architectures are kind of this fusing together of different models in a way where you can combine the benefits of all of them. And the multimodal projector is actually typically a very small model. And really, it helps facilitate taking the image embeddings from the image encoder and sometimes compressing them and also just mapping them into the text input space. So if we kind of put this all together, if we go to the next slide, Tim, is you can see with like the Qwen VL model how this practically works. So here the multimodal projector is just subsumed within the vision encoder, but you can put in images, you can put in videos, and videos are just kind of split up into frames. And you put those things into the vision encoder, and out you get a bunch of actually tokens, just like the text tokens. So they get input to the model at the same level as like this text caption that says images and videos here. And then there's a bunch of tokens reserved for the visual inputs, and then you can have text after that. So you can have interleave text and images. You can have multiple images. And one interesting part that you can notice here is actually the image resolution itself makes a big difference to how many tokens get allocated to that image. And so, like, in a way, it decides how much information about that image is going to be preserved by the encoding. And so this is a knob that's often like an important thing to tune or set to both balance like context length as well as quality. And also latency, as we'll see later, the resolution of the image can have a big impact on even the vision encoder portion forward pass. So now, like, what can VLMs be used for? What are the common things people are using them for? This is Arnav, one of our team leads, and we've made a little example here. Um, Visual question answering, I think, is kind of the most general. and broad use case for VLMs because it's just like, it's kind of like text-based question answering. It captures a lot of tasks under that label. And so in this task, we're just asking the VLM to see if these images are different or not. And what you'll notice also is that we can prompt the model just like we prompt a regular LLM. We can have it output a structured JSON with different attributes. You can have it do chain of thought. A lot of the VLMs do some sort of like basic reasoning when they talk through things. So in that way, it's not so different from interacting with your traditional LLMs. And yeah, just someone asked in the chat, which I think is a good question, is it a deterministic setting? Like when we're talking about each image giving a different number of tokens. And yes, it is a deterministic setting, but it's very model dependent. So the Qwen VL model will get a different number of visual tokens for the same image that say like a Gemma model would. So this is again like part of the complexity of VLMs that um, Predibase actually hopes to help you solve and decide good numbers for these and also manage what GPUs you need for this and that sort of thing. And
Uh,
returning back to the use cases, the another use case we have here is image captioning. And this one is like generate a caption for this image. And one thing I like to point out here is that you can like include a URL. And again, you can still provide tools to a VLM and they can still like search the web. They can do all sorts of things that the normal LLM can do since they just output text. And finally, for video or image analysis, I think video is something that is unexplored and it's a bit challenging to set up, but is going to become very popular in the coming years. So here's an example where we can ask the model to just analyze what's going on in the video in a sort of open-ended way. And so it says the video captures a moment in the park where this deer is walking on a path and so on. So the QuenVL model we looked at will support that, but that model doesn't take it into any audio. So there's also models being developed that take in both the video and the audio portion of that video. So really, like kind of the thing I want to take away here is that you can use VLMs for anything an LLM can do, plus you're adding the ability for it to see. So this is like from a paper MMT Bench where they create a whole vast number of tasks for VLMs and evaluate them on them. And just from my personal experience, like I use VLMs, the vision abilities of models all the time. Like one thing I do is I use it to take pictures of like my food and try to estimate like the macros as I'm on my gym grind. Or I use it to like take pictures of LaTeX formulas and translate it to text. So I think it's actually very, very useful, especially when doing things in the real world. But VLMs are not perfect, and I think Um, my kind of headline takeaway for that is the out of the box vision capabilities are not as strong as the raw LLM text capabilities. I would say that like even that your top open source as well as closed source LLMs are better or as good as humans on like a significant number of text-based tasks, especially if you prompt them well and if you like get the right context to them. But with vision, I would say humans are still much better at seeing and using their vision to analyze images than current day LLMs. So, I think this is a good example, right? Like, um, they're essentially very kind of biased and connected to what they've been trained on. So, um, for example, like they're not trained on that much like handwritten text like this. So I think if we take a closer look at this example, right, like it's pretty hard to read this text fully for what it is. But I think with the multiple choice, it's pretty clear that the first part ends with my dear. So it's clearly B, C, or D. And then it's also clear to us that it says Peggy's eyes filled. And it definitely doesn't end with swelled or with tears. So clearly the answer should be C. And I would say this is a very easy problem for humans. Like even a child could get this right. But for these vision models, just out of the box, right, without any sort of fine tuning for this task, we see Gemini Pro, which is like a state-of-the-art model. Um, failing in this task completely and selecting D. It thinks that the word width is in there and it's not in there at all. And then intern VL is a open source model that's also one of the top open source models. And it also makes a mistake and thinks it's D. So, and GPT-4 gets this one right, but this benchmark actually shows that the performance is not necessarily that one model is going to make mistakes and not make um, not they'll make different types of mistakes, but they're all prone to errors where we expect them to do a lot better to match human capabilities. Another interesting piece of work called VLMs are biased, if you want to look at the research paper, evaluates like the top models right now, even the O3 and O4 models, and they come up with a different way of evaluation. They basically take a task of counting things within popular subjects. So count the number of stripes in the Adidas logo, or count the number of legs on a Puma, right? So all these models get 100% accuracy when you give them these sort of problems. Um, but if you actually change them a bit, you create what's called counterfactual images. So let's say you make an Adidas like logo, like columns E and F, where it has four stripes instead, which, to us is obvious and like we wouldn't necessarily make this mistake. Um, Most of them get this wrong and the accuracy drops all the way to 17%. And I think one also thing with VLMs is it's like harder to use prompting to kind of just force them to get these type of problems right, because oftentimes because the prompt is not going into the vision module, it won't modify how the image is actually encoded. So you sort of need to actually be able to update the weights sometimes to fill in these performance gaps. And so open source models have in the vision space, I think are actually even more competitive with closed source models than in just the pure text space. And one big reason for that is a lot of open source providers have released models that are specifically vision language models that might not be as strong on pure text to text tasks, but are actually better than the all-in-one closed source models of similar size on vision tasks. So we see here the Qwen VL model is, for example, beating 4.0 and Claude Sonnet on essentially all these visual benchmarks. And a lot of these are like visual understanding and require some level of intelligence. They're not just, very simple like image classification or anything. So if you have specific tasks that the model is only going to do vision for, or not only vision, but you're not going to use it for like solving, I don't know, like some sort of math problem, then it actually might be a lot better and you can get better performance out of the box with using a VLM with a smaller size model and a faster model. Another reason you might want to use VLMs is to fine tune them for quality when you're using use cases that require a lot of accuracy as well as high reliability. As we saw in some of the examples, there's some fairly easy tasks that the models get wrong, but I don't think they get them catastrophically wrong. I think they're close. And I think in a real production scenarios, you want to be able to fine tune the model to get consistent performance on these things. So I think one like common place would be like in medical domain, you really need very high precision and reliability. And if you actually look at the open source releases for very few people are using just um, out of the box models for medical tasks and getting the performance they need. And so you often need to fine tune them a bit or design models for these domains. And one example of this is a science QA task, which is, multimodal questions about scientific topics. Like there's an image here in the bottom example, which type of force from the baby's hand opens the cabinet door, and there's an image of it. And so on this task out of the box, GPT-4 was getting around 70%. And the authors of this work on fine-tuning lava for science QA were able to get like 91% accuracy. And for reference, these lava models are on the scale of like 10 to 20 billion parameter models. So they're going to be also very fast and not going to require a significant amount of GPU resources to run. Now, coming back to the image resolution, um, this is also an important variable in VLMs. The image resolution actually affects, as we saw, how many tokens are kind of attributed to that image. And so intuitively, it also corresponds to how much information from each image is passed to the language model backbone, which actually does the text generation. So scaling in that previous example, using the higher resolution image got the right answer, while the lower resolution didn't. But um, you can also get much higher latency. So here we see on the x-axis input image resolution, and on the y-axis latency. And it's also split between the vision part and the LLM prompt encoding part, which is what pre-filling means. So we can see that like as the input image resolution increases, the LLM pre-filling increases like fairly linearly because it's just essentially getting more tokens into its prompt. But we're used to like having even tens of thousands, hundreds of thousands of tokens in LLM prompts. But the vision model module, even for just like a 1.5 billion parameter model, the high resolution images start um, kind of dominating the latency with just the vision encoding. And in our own experience, we found that like to get good performance out of low resolution images, fine tuning goes a long way because there's not really many other knobs you can tune, such as prompting isn't really an option to deal with like the resolution problem. So kind of one another reason to fine tune VLMs, which these last few slides have talked about, is just latency and cost. Like I don't know if people have regularly used like ChatGPT or whatever their favorite closed source models are for multimodal tasks, but the time to first token is like significantly higher, even compared to like using a long prompt. And this is attributed to like sending the images over the web, using having the same really large, hundreds of billions of parameter LLM backbone used regardless of the visual task. And as we show, like more images and larger resolution images, the vision latency can add up a lot. And so like combining open source models, which are specifically used for vision, plus fine tuning them means you can get the same performance with smaller and faster models. So on VLM specific struggles, right? Like I think the blockers to kind of deploying VLMs yourself or training them yourselves um, create new challenges compared to just using LLMs. Like the ecosystem itself is like less developed. I think if you go on Hugging Face and stuff, you'll see that it's actually harder to find out how to even run these things and train these things. Different VLMs require different inputs and different pre-processing logic and have different like code snippets on Hugging Face on how to use them, right? Figuring out how to correctly format the inputs can be time consuming and error prone. You It's a lot more low level compared to a lot of the rest of the developer experience currently is for using LLMs out of the box. And then you have to also handle like the data. It can be larger and a lot of moving parts between image storing, how you like send that into the image to the model, and new constraints for like hardware based on serving these things. So um, a combination of all these things um, is why we think you should use Predibase to help you with tuning VLMs in a way that is just as easy as tuning LLMs right now. So we have integration with AWS for easy data access and managing your credentials. And we have custom like data pre-processing and collators that handle image resizing and format inputs in the right way. And we kind of update that for new models as they come in. So your interface is still the same abstraction regardless. We use LoRa-based fine tuning, which we validated on like real world examples, is being high quality performance as well as significant savings in memory usage. And we've also we also automatically handle like the infrastructure, like setting up which GPU, spinning up the GPUs and down, saving all your checkpoints. and transitioning from a training to a trained model to then serving and deploying or evaluating that model. So just to recap, what Predibase can help you with when it comes to VLMs and LLMs as well is, currently like data can live in different systems and there's different libraries you want to use and there's performance trade-offs like there's onslaught, there's Hugging Face, but you just want the fastest thing. You want the thing that will work the best for the model you want, and you want to not have to worry about setting up the GPU, setting up the dependencies, and like managing the cost of that. And we handle all that stuff for you, right? We make it easy to add your data connected in one place. We have a bunch of optimizations and to make fine tuning as efficient as possible. And we allow you to serve in a serverless fashion with auto scaling. We have GPUs from all the way from like A10s to H200s available, and you can serve even multiple models on one GPU. So you think your vision model, you know, should be able to tell a Chihuahua from a muffin here, then you should try out Predibase for fine-tuning your VLMs.
Cool. Thanks, Amir. Uh, I'll take over from here. I'm Tim. I'm another ML engineer on the Predibase team. And I'll be taking you on a little demo and a little bit of a toy example right now for VLMs in Predibase. So we're going to take a look at this toy task that you can get off of Hugging Face. It is Pokemon card captioning. So over here on the left, we have a Pokemon card. I want to gather the name, the HP stat, the set name, and a caption given this image of a card. So the really tricky one here, I would say, is going to be that set name, because this is what the main interaction is between image and text, because the only thing that indicates set name is this image in the bottom right corner. Sometimes it can shift position on the card. But we want to see if, without any kind of mapping, any explicit like I said, any explicit mapping there, can we get sufficient accuracy on this toy task here? Um, so effectively, uh, what we've done here is we've just created a data set with all of this information back here. We pass in the image, we pass in uh, HP name, set name, and a caption in as the effectively as the label. But the way we do that is by preparing our data set in the following format. So what we do is we create messages. So anyone who's familiar with, for instance, like the OpenAI data formats for VLMs, this is going to be very, very familiar for you. We define a set of messages using role content pairs. So your role can be system, user, or assistant. And then your content for each message is going to be a list of mappings. The type can be text or image URL, depending on which one you're passing in. Um, so here on the right, you'll see that the first message that we have in this small conversation is a user message. And we pass in the image URL. So in this case, it'll be the image of our Pokemon card. And then we pass in a prompt. Similarly, the second message is going to be our assistant, and it just passes in the completion. So I'll also just note really quickly that order does matter when it comes to the image and the text. So for instance, if I were to swap these here, so I get text first and then image, that's how the model would receive my messages. So be sure to keep that in mind when you're fine tuning and when you're querying. But I'll give you all a little bit of a closer look as to what this looks like for our task. So I pass in our image URL here so that you can see exactly what that is. The model then gets passed in. You are presented with a Pokemon card. Please provide the name of the Pokemon, its HP, the set name, and a caption. And here in the assistant, this is what I want to teach the model to generate. So in this case, this acts effectively as our label. And it returns this JSON object of the name, the HP, the set name, and the caption. So this is what our data set looks like. Uh, and with that, I will show you just a really quick walkthrough of how to do this in Predibase itself, just so you can see how easy it is for us to do so. So over here, I have my dataset in Predibase. The really important column here is messages, because that is what the LLM sees in Predibase. We take this messages column and we pass it into the model. So here, it's not formatted as pretty as it was in the slide, but it is the same content effectively. I pass in the content, I pass in the image URL, the prompts, so on and so forth. And then I also have this extra Q at the end that says role assistant over here. This is the assistant message, and so we just train over this entire thing. You're also able to pass in a split column, so you have your evaluation, your train splits here, just to see how things go. Next, I have this VLM webinar adapter repo. So this is what it looks like when you come to create a new adapter. Over here on this adapters page, you just create a new repo and you will have your models here. And basically, I'll just click on this new adapter here. You can go through here. I just have one already set up for y'all to take a look at here. So we have our data set here is Pokemon JSON response train. And then all you need to do is select the large language model to fine tune. In this case, it's not a large language model, it's a vision language model. So Qwen 2.5 VL 7 billion instruct. And I'm just going to select LoRa. Don't worry too much about what Turbo LoRa is right now. That's not something that we currently offer for VLMs, but it is effectively just our speculative decoding offering for large language models for anyone who's interested in that. Uh, we're going to just do SFT as our fine-tuning task. Our Predibase will recognize that this is in fact a vision language model and properly adjust for that in the back end there. And here we can select a few different things. So we can take a look at setting the adapter rank. We also can set our target modules of what we want to fine tune. So in this case, I can add all of these target modules here just to fine tune this model, perhaps get better results if I do. And here I can also set epochs and learning rate. Finally, we also have this enable early stopping, which effectively just says that if validation loss plateaus, we can just stop the training right there. And all you do is just hit train. And there we're training. I do also have a model already ready for you to take a look at. So I'm going to stop sharing this real quick, and I'm going to share a quick inference script with all of you here. So what you can see here is a quick inference script. Effectively, what I do is I just pass in my API token here. And all I need to do is run my deployment. I set my deployment name. I set my adapter version here. I define the same set of messages that I do. This is from our evaluation set. I pass this through to our OpenAI endpoint here. And I use chat completions to just be able to pass all of this in. And then I can just run inference real quick. This will then run and generate our output. If you want to compare here, I'll zoom in a little bit. We do, in fact, have Arcanine here. The HP stat is correct. The set name, you'll have to kind of just trust me here, but that set name is actually also correct. And the caption is fairly accurate. So with this, we're very happy with how this model is done. So this is just an example of how to run inference with your VLM in Predibase. And now we return back to our here. One moment. Let me just get back to our slides. Here we go. So you might be curious how well the model does overall. You saw just an example of what we got. We did compare this to just OpenAI's GPT 4.0, I believe. Sorry, 4.0, my bad. Here, this was our accuracy. I believe this was either GPT 4.0 or GPT 4.0 mini. But our name accuracy was at about 90%, and the HP accuracy was about 90, was almost at 100%, even with just a closed source model, which is to be expected given that those are printed pretty prominently on the card. The main thing here that we see though is that the set name accuracy is only at about 15%. keep in mind that we did not provide any explicit mapping. I will also say that if anyone's interested, we did also add an extra thing to the prompt into the OpenAI model just to tell it specifically to provide a JSON output. Um, and here, that accuracy drop has increased considerably. So the name accuracy is also increased up to almost 100%. HP accuracy is still at basically the same level, and the set name accuracy has increased to about 96%. The baseline metrics, this is basically the OpenAI versus our fine-tuned model. If I remember the baseline metrics correctly, they're not on the slides, but the set name accuracy dropped, I think, to like below 10%, if I remember correctly. But yeah, we very happy with how these accuracy numbers have improved. Specifically, also, although not shown here, the captions also did become considerably better, and they did follow the format of our fine-tuning data set a lot more closely, which is to be expected. Uh, and here we have one more little case study that we did at Predibase, um, perhaps a little bit more of a real-world task. The task is effectively, on the left-hand side here, we have a reference image. And on the right-hand side, we have a grid of images that are, for instance, pictures taken from different angles, pictures taken with different lighting. Here, that's not shown. This is kind of just a little bit of a toy example here. Uh, and we want to determine which of these images on the right match or don't match the reference image on the left. So in this case, it would be these three in the bottom right-hand corner don't match the image on the left. The model would then output effectively the indices of the images that were mismatched. So in this case, in images 5, 7, 8 don't match, thus the model should return a list 5, 7, 8. One of our concerns with this uh, basically this approach is that we are concerned about the image patches. The reason why we had sent in our images this way instead of comparing them one-on-one is just efficiency. We wanted to see if we could show noticeable improvement in training with fewer data samples. So effectively tamping down the number of tokens, tamping down the number of examples for cost savings as well. So this goes in as one image. But the main concern that we had here goes back to effectively image resolution, like we were talking about before. Back to what Samir was saying earlier, the model effectively segments our image into image patches. And this is what goes into our, like each of these patches will effectively represent a token eventually, but this is what goes into our image encoder. The problem is if we get a patch that looks like that. We were concerned that maybe this would not show enough information, that the model might get confused on patches like this, especially when comparing a grid versus a reference image. So while this was on our mind, we decided to test this out anyway. And the results showed surprising robustness. We take this to mean maybe one of a few things. It's possible that just due to the bidirectionality of the image encoder, that each image patch is able to attend to all other image patches and thus gain enough context about the image as a whole to determine differentiation between the reference image and the images on the right. Also, just simply because all of the images are effectively in the same orientation per sample, that's during fine tuning, the model has just learned to attend to the appropriate patches. Regardless, fine tuning ended up giving us a lot of lift. So in this case, GPT-4o got an accuracy of about 84.33%, precision about 75%, and a recall of about 60% for a total F1 score of 67%. Whereas the base model got an accuracy of only about 77%, with a precision of close to 75%, but a recall of only about 4.5%. This is just due to dataset imbalance. So the binary F1 score ended up being very low at only about 8.5%, whereas our fine-tuned model ended up bumping up the accuracy by about 13 points. The precision ended up increasing about 7 points, and the recall jumped up by almost a whole 70 points. This gave us a binary F1 score of 77.72%, which is over a 10% increase from the binary F1 score of GPT-4o. So ultimately, hopefully we've shown you here that fine-tuning your VLMs does give you a very significant lift over both the base model and potentially a lot of the enterprise models that are available today on specific tasks. So with that, I want to thank everyone for attending, and I'm going to open up the floor for Q&A.
Awesome. Let Samir jump back in. One, encourage folks to put their questions into our Q&A panel, so it's easier for us to manage, but we'll also keep an eye on the chat. So I know, Samir, you've been answering some of those questions, but let's answer them for the group as well. So someone asked, as we mentioned earlier, the clip model or transformer. Their experience with them, their results were quite far off from when they sent the image to Claude and asked similar questions. What would make Predibase a differentiator in training open source models to come closer to on par with commercial models? What do we offer? I know we talked a little bit about it, maybe just to kind of recap. Oh, Samir, you're on mute.
Thanks. So first, this person was asking about Clip, and so I think one thing is that like Clip is a very old model, and so just using a Clip model for visual tasks is going to be behind Claude, but it's also going to be well behind like the latest Qwen VL models. And I think if they were to try those models, they would see that they would perform quite well, as well as tuning the model could get you a lot farther. And I think Predibase would make it easy for you to both try out these open source models, try out a variety of them, as well as update those models to get better at a specific task. Now, someone else asked about they use VLMs and they find that the patch size has a large effect on the accuracy. A VIT patch size of 16 by 16 is better than 32 by 32. And they said one issue with the models they've worked with, like ChatGPT's 4o, is that it's not clear what the underlying patch size is. So I think this is one benefit of open source models. You can just go read what the patch size they use is, and you can modify how many how the resolution per image. And so, for example, the Qwen models use like a 28 by 28 patch size. Um, but it is model specific and model builder specific. This is something they tune during the training process. Someone asked on the image quality. So they asked, is there a guideline on how good quality an image is for VLM, while not putting too many tokens required? So this is again a model specific parameter, like how much each image gets compressed, but they will all be in like a similar sort of trend. So like if we take the Qwen models, for example, um, each patch size is 28 by 28, which means every 28 by 28 pixels corresponds to one token that's going to go into the LLM roughly. Um, and so when you use like the Qwen VL models with Hugging Face or whatever their recommended default settings, then that limits to 4,000 images per token, but you can set it all the way up to like 16,000. And but I would say like something around a few thousand is very reasonable. For example, using 4,000 tokens corresponds to a 2,000 by 1,600 image. So that's like a fairly large image, and that image will be kept in full resolution. So, um, yeah, usually the defaults are pretty decent, but then what I really recommend is start with kind of like the default resolution. And if you only notice that it feels like the model is getting things right because it can't see certain details clearly, like I think in the Pokemon example is a good example. If it seemed like that set figure is kind of very small. So if it felt like for some reason the model couldn't differentiate those, you could try increasing the resolution potentially. Um, or like cropping certain parts. So there's like a lot you can do on like what how you present the image that can make an impact to the task.
Right.
There's also been a lot of questions. Oh, sorry, Tim, were you going to add to that?
No, no,
For
Michael, take it
listeners?
away.
Sure. A lot of questions actually about, like you mentioned, supervised fine tuning. A lot of questions about reinforcement, fine tuning, reinforcement learning. Uh, one, have we tried that? Do we have opinions on would it work well? And then, levels of support for that. So curious your guys' thoughts.
Yeah, I can take that. Absolutely. We have not actually experimented yet with RFT for VLMs, but it is definitely on our docket as something we want to explore because we think that there is a lot of potential there for just improvement. In particular, just because I think uh, there are a lot of ways we can design some fairly interesting reward functions for VLMs that integrates both the image and the text outputs. Um, but yeah, hold tight. I think you might see that coming soon in the Predibase product.
Yeah,
Uh,
I think it's a very promising thing. There's not a lot of models out right now that have done that, but like there's a lot of research that's coming out on basically adding reasoning and RL to vision models. And someone asked about vision language action models, like VLMs that kind of do actions, and RL is also very important there. So yeah, I would say that's like a promising area that's like developing right now. And um we support RFT in our platform, and using VLMs for that is just a bit of like a engineering challenge. It's not like um a whole new thing we need to build.
Yeah, Samir just took the words out of my mouth. I think we already offer GRPO for LLM, so if you haven't seen that, go check it out. Um, but no, I think it's the level of effort to get VLMs for with GRPO setup is probably smaller than like starting from scratch there if we didn't have GRPO already in the product. So hopefully we'll be able to start experimentation with that relatively soon.
and if you're interested, it's, valuable use case, come talk to us because maybe you could become a design partner. Um, some other questions. One about accuracy in chat. How does quantization of the model affect fine-tuning performance and
Uh,
accuracy?
yeah, so basically all of the models that we train in Predibase are with QLoRa, generally 4-bit QLoRA. So all of our models have tended to perform very well. I don't think we've really had any complaints regarding model quality and all of our exploration in the past, whether that be if you're familiar with our really early on LoRa land or our fine-tuning leaderboard, any of our explorations there, all of them have shown that 4-bit QLoRa ends up with still very robust results. Um, so with regard to to the quality of the models that come out, I'm confident in quantized LoRa training.
Great. I also just put a link to our fine-tuning leaderboard. It doesn't have VLMs in there, but we did take, a dozen or so of the most popular models, fine-tuned them across 30 different data sets, and you can see the results and kind of benefit you get of fine-tuning. And just sort of like broad strokes speaking, we've seen like 85%, if not more, of our models when we fine-tune them across these different use cases outperform frontier models. So you can really get incredible performance. And oftentimes, depending on the model size and what your task, it can be as low as like $8 to fine-tune a model. So it's not an expensive activity, and you end up with a model you own that's smaller, faster, right? And significantly less expensive than a large commercial model. Someone also asked, like, um, are we similar to Unsloth? I guess I would just say is like Unsloth, great open source package for fine tuning. Predibase, what I'd say is sort of differentiated or in some ways similar. We do offer a robust set of, as Tim mentioned and Samir, post-training techniques from supervised fine tuning to reinforcement fine tuning in a managed service. So what that means for you is you don't have to worry about all the infrastructure. You're going to get all the optimizations, the latest ones from research. We're staying on the cutting edge of training techniques and serving techniques, baking it into the platform. And so we make it really easy, right, and very developer friendly to go fine tune your models and do that on a very reliable infrastructure. And then with a click of a button, put them right into a production environment so you can serve them, and then keep iterating continuously with all that headache of sort of doing that yourself. So Unsloth is great. What I'd say is like, anytime you're using open source, you're then going to have to manage the infrastructure, get the serving, stack as well, and bring it all together. So we try to make that as easy as possible so that you can just build really cool models. I don't know if you guys have anything to add vis-a-vis Unsloth.
No, it's just like we effectively are, I'd say, uh, a step not quite removed from Unsloth. Effectively, just a, like you said, Michael, we help abstract a lot of the difficulties away from the user, and we just make that overall workflow of get your data, fine tune on it, serve your model, significantly simpler.
Awesome. And then there's also on the serving side a ton of optimizations we built in, like multi-lower serving, so you can serve many fine-tuned adapters on a single GPU. We have turbo lower, which they reference, which then gives you the benefit of increased throughput through techniques like speculative decoding. So on the serving side too, you're also going to get a more efficient, faster experience. Um, how does the volume of images and the fine-tuning effort improve fine-tuning, like the number of fine-tuned images or your data set?
Yeah. Uh, so of course, I think this has been just common for ML training, like model training through like for as long as I can remember, is that generally, if you have a lot of data, that tends to be a pretty good thing for your training. I will also add the caveat of even if you, I'm going to assume that this means more training samples, not necessarily images per sample, but the caveat is that the image data should be fairly high quality. So the pairs of image and text. What we've noticed is even if you give us a lot of data, if it's, for instance, really imbalanced or the quality is just not differentiated much between samples, uh, that can actually degrade model quality. So what we actually did with our training for that last case study is we actually had to rebalance the data sets a few times. We've and by cutting down some of the numbers of samples that we had, we actually improved the model pretty significantly. So in that case, I would just say make sure that your data is, like I said, high quality. And if you maintain that quality throughout your data sets, the more samples I would say probably will give you better results.
Awesome. Appreciate that. Someone's asking about how we validated the results, the metrics that we obviously had the metrics you mentioned, Tim. Do we also do like some level of human validation or maybe just general philosophy on how you're doing the evaluation of the performance of the fine-tuned VLMs and role of human validation?
Right. So human level that does tend to just mean like we do sanity check our results for a lot of these just to make sure the model isn't, for instance, cheating. This is something that we definitely wanted to also take a look at when it came to GRPO to make sure that our models weren't just cheating the reward functions. But in this case, for instance, the Pokemon toy data sets, I manually scanned through the captions that were being generated to make sure they were in fact like fairly high quality. Um, is of course that level of rigor will differ depending on the scale of your use case. But absolutely, I agree that having some level of human in the loop is fairly important, especially if the use case is uh, very critical or relies on high accuracy.
Got it. Um, have we worked with any use cases yet that involve like real-time video and capturing anomalies in that yet?
We haven't touched video yet, but yeah, another direction that we really want to explore.
Are there any like hot use cases you're seeing specifically with some of the companies we're talking to, like in speaking in general, broad strokes?
I can't think of anyone specifically that we're talking to who's asked for anything in particular regarding videos. I think we're in the time period where a lot of our customers are starting to ask more about images. Um, because of course, initially we had the huge craze of like LLMs, people want to talk about the text space. Um, and as VLMs have picked up in popularity, like Michael said at the beginning of our webinar, um, companies have started to adopt that and they've been more keen on taking on vision language models. But I don't think the video craze has quite caught on yet with the customers we're talking to.
Sorry, I meant more on the just core image stuff. Are there certain like use cases you see are emerging as like a frequent pattern or stand out to you?
Uh, I think a lot of it does come down to like either image captioning or just answering very specific questions uh, that, like for instance, the medical image uh, question answering that Samir showed earlier. Samir, do you have anything that you remember specifically? I understand that there's not a ton of specifics we can go into on some of our customer details.
Yeah, I think one big one is just like aspects of like kind of classification, but with a little open-ended aspect to it. I
Mhm.
think a lot of people are trying to bring VLMs into existing pipelines to like filter things for downstream, like larger pipelines or like content moderation. It's like a clear use case where VLMs can like offer a lot of value over existing methods.
Yeah,
Okay,
content moderation. Yes, definitely one of the big ones too.
absolutely. Yeah. What about any just general guidelines you provide on sort of data set size, number of epochs, layers to train, adapter ranks when you're working with VLM for fine tuning? Is there a set of sort of best practices there?
I would say it's very similar to the best practices for like LLM fine tuning. Um, but we have found in our experience that you may need to train them for longer. Like, I think because like VLM, I think a lot of the times the tasks you're training a VLM on, they're just not necessarily as good at it out of the box, the more domain specific it is. So, um, potentially more epochs and capacity, but it's very task dependent, just like with LLM tuning. And I would say apply the same kind of intuitions and heuristics there to start with.
Yeah, actually, just looking at the wording of the question, I think that order is actually really good. Um, is that if you can increase your data set size, do that first. See how the model quality increases. If that doesn't work, number of epochs or layers to train, those like your target modules, those two are probably the next two I would take a look at. And if that doesn't work, take a look at the adapter rank. I think that's actually a really good order to iterate on. But I'd say that usually data set size or data set composition ends up being the largest determinant like determining factor of performance.
Got it. And I know we're wrapping up here. Yeah, that's this last one. What is a major failure use case you've seen in training, particular cases and real world examples of VLMs? Anything you can speak to there?
Major failure cases. I actually haven't run into anything that I would necessarily consider a failure. I think that is something that might warrant more experimentation. Uh, Samir might have a bit more to say on this, but I think probably anything that where we're going to try to challenge a model's biases, like we mentioned earlier, might give us a little bit of trouble. Um, but no, I think we just need to experiment more before we can start talking about like our like major failures are.
Yeah, I think I don't have one specific for that's specifically tied to training, but I think you can also extrapolate to training just from using like just VLMs, even just for like just an inference, right? Like they're like kind of hard to steer with the prompt relative to like LLMs. Like even if you tell it like it's hard to prompt it to look at the image differently is kind of how I would describe that and see things in a different way. So um, yeah, I find that VLMs are sometimes less flexible in given a certain image. So actually, I think that's something though that training would help you with, but having the right training data is probably the biggest challenge there.
Awesome. Well, I know we're at time here. A lot of great discussion, a lot of great questions. Really appreciate everyone joining us today to talk through sort of VLMs, how you can fine tune them, the sort of experiments we've seen, how to get started. And I really appreciate Timothy and Samir for, as our experts, guiding us through everything that you've learned on this journey. So, again, if folks are interested in trying this out, you can try the platform. You can also just email us or reach out on our site. We have a link to a demo. We're happy to talk through your use case and help you get started. So, with that, I'm going to wrap things up. Thank you again, everyone, today for the great discussion, and we'll catch you in a few weeks for the next one. Take care, all.
Thanks all.